What if the very elements we can't live without, the fundamental building blocks of our world, also held some of the greatest potential for harm? It's a complex paradox, and today you're joining us on a nuanced world of metals.
That's right. Our mission is to cut through the noise, separate the science from what our sources call these emotionally charged labels,
Yeah.
and give you a clear, comprehensive understanding of these omnipresent elements. We're drawing heavily today from the rich insights found in Mining and the Environment by Dr. Karl-Heinz Spitz and John Trudinger.
Okay, so let's unpack this. When we talk about metals, what exactly are we defining? Chemically, all known matter is made up of 109 elements
Right.
that cannot be broken down further, and these are broadly subdivided into metals and nonmetals.
And here's where the data truly surprises you. While the vast majority of known elements are indeed metals, 86 of them, in fact.
86.
Yeah, but get this, over 80% of the Earth's crust, the very layer we dig into, is actually made up of nonmetals.
Wait, really? 80% nonmetals?
It's a profound twist, isn't it? The ground beneath our feet is overwhelmingly not metallic.
That's a mind-bending fact.
Yeah.
Okay, what characteristics define a metal then? Physically, we typically think of their high thermal and electrical conductivity,
Has shine.
that distinct metallic luster, their strength, and their ductility, which means you can draw them into a wire.
Exactly. And from a chemical perspective, it's an element that readily gives up one or more electrons to form a cation in an aqueous solution.
Okay.
And by that definition, about 0 elements fit the bill. Now, you'll often hear the term heavy metal thrown around, especially in environmental discussions. But it's actually an inexact, almost misleading term.
It sounds like one of those emotionally charged labels our source mentions. People often use it as like a catch-all for any metal they perceive as toxic. Is that why it's best avoided in scientific discussion?
Precisely. It can refer to metals with densities above 5 grams per cubic centimeter, which applies to 38 elements, or those with an atomic number of 20 or greater. More commonly, though, it simply denotes metals that are toxic in low concentrations. But for environmental studies, using the neutral term metal avoids any inherent bias and allows for more precise discussion of their specific properties and impacts. It keeps things clearer.
So metals are everywhere in nature, but their distribution isn't uniform at all. You mentioned the crust. Only 8 elements make up over 98% of it by weight.
That's it, just 8. And silicon and oxygen account for about 2/3 of that alone.
Wow. So all the other metals are crammed into that remaining tiny percentage.
Pretty much.
Yeah.
And if you're looking for economically important metals like gold, silver, copper, lead, zinc, tin, nickel, or platinum.
The ones we mine for.
Exactly. They typically make up less than 0.5% combined in any given rock. They truly are rare finds in the Earth's overall composition.
It's remarkable to consider that life on Earth has evolved not just with these metals, but often because of them. Some have become absolutely crucial for survival.
Indeed. Life didn't just pop up in a metal-free world. Organisms have developed incredibly complex mechanisms for their uptake, excretion, regulation, and even detoxification.
Like adapting to the environment they found themselves in.
Absolutely. Some essential metals, like sodium, potassium, magnesium, and calcium, are present in large concentrations in our bodies. They're vital electrolytes.
And then there are the trace metals, normally less than 0.01% of an organism's weight, but they are incredibly vital. Things like iron.
Iron, yes, essential for oxygen transport in our hemoglobin. Without it, anemia. Or manganese for sugar metabolism. Zinc is crucial for enzyme function in protein and nucleic acid metabolism.
Cobalt too, right? For vitamin B12.
Spot on. Cobalt's a core component of vitamin B12, needed for hemoglobin formation, nitrogen fixation. Molybdenum is involved in electron transfer processes.
And beyond these ones that all life needs, there are others essential just for some organisms.
Yes, like nickel, vanadium, iodine, silicon, and boron. And take chromium, for instance. In its CR3 form, it's involved in glucose metabolism, working with insulin.
Okay, so that's the good side of chromium.
But it's CR compounds. Those can induce skin sensitizations and are even assumed to be carcinogenic.
Wow. That's a profound realization. The same element can have both a beneficial and a profoundly harmful form depending on its chemical state, its speciation, as you might say.
Exactly, that's a term we'll come back to. So for essential metals, it sounds like our bodies are walking a tightrope.
Yeah, it does.
You've hit on a critical point. For essential metals, both a shortage and an excess are detrimental. Your body needs to regulate them within a very specific concentration window. Too little can cause deficiency problems, like anemia with iron. Too much can be toxic.
So it's all about balance for those ones.
Precisely. But for non-essential metals, think arsenic, lead, mercury, cadmium. There's no known benefit.
None at all.
No. For those, only excessive environmental concentrations cause adverse effects. It's purely about managing exposure and minimizing their presence in us and the environment.
That distinction really clarifies things. Okay. Now, let's talk about how these elements get released into the environment, because this is where human activity dramatically changes the equation, right?
Absolutely. And a key thing to remember, unlike organic compounds, metals cannot be chemically or bacteriologically degraded. They don't break down.
They just persist.
They're persistent. They simply exist in various physical and chemical states. So when we mine, metals are unavoidably released.
How?
Well, from mining wastes, the primary mechanisms for their release are things like leaching into ground and surface
Water running through the waste rock.
Exactly. Fugitive dust emissions blowing off piles and solutions from the tailings ponds. And metal solubility is highly pH dependent.
Meaning
A decrease in pH, what happens with acid rock drainage, when water reacts with sulfide minerals.
right, it gets acidic.
That will significantly increase the leaching of most metals. They dissolve much more easily in acidic water. Metal hydroxides, for example, are generally more soluble than metal sulfides under those conditions.
Okay, so if the water becomes more acidic, more metals dissolve and spread. We also see air emissions, you mentioned.
Yes, from primary smelting operations, volatile species escaping, and stack emissions from the processing plants. And of course, a smaller portion ends up in solid waste products like slag and wastewater sludge.
But here's the counterintuitive truth you hinted at earlier about metal pollution.
Ah, yes. Only a small fraction, relatively speaking, of the total metals released to the environment originate directly from mining and mineral processing itself.
So where's the rest coming from?
The main sources are actually metal usage. Think about leaded gasoline used for decades globally.
All that exhaust.
And the final disposal of discarded metal-containing products, things thrown into incinerators or landfills. That's where the bulk of the release often happens.
That's a huge takeaway. It's not just the digging, but how we integrate these materials into our lives and then discard them.
Precisely. And it gets even more complicated because some metal combinations can actually interact. They can be more toxic together. That's synergistic.
Like 1 + 1 = 3, toxicity-wise.
Yeah. Or sometimes less toxic, antagonistic. Our sources point to examples like nickel and zinc, and copper and cadmium, where these combined effects can happen.
Okay, and you mentioned speciation earlier, the form the metal takes.
Yes, speciation is absolutely crucial. Think of it this way. Water is H2O, right? But ice and steam are also H2O.
Same elements, different forms.
Exactly. Same elements, vastly different forms of behaviors. Metals are similar. Their toxicity isn't just about the metal itself, but the specific chemical form it takes. Is it an ion? Is it bound up in an organic complex?
And that affects everything.
It profoundly affects how it moves through the environment, how easily it's absorbed by living things, its bioavailability, and ultimately how toxic it actually is. The same amount of metal can be harmless or deadly depending on its species.
That analogy helps immensely. Okay, so from these broad categories and processes, let's zero in on some specific metals. Each one has a fascinating and often surprising story. It's wild to think that by the 18th century, only 12 metals were known.
Just 12.
Today, there are 86. But those 7 metals of antiquity, gold, copper, silver, lead, tin, iron, and mercury, they truly form the basis of civilization.
They certainly did. Let's start with lead, Pb. It's deeply embedded in our language even.
How?
The English words plumber and plumbing come directly from the Latin word plumbum, meaning lead.
Because the pipes are made of lead.
Exactly. Ancient Roman water pipes were made of it. And some historians even hypothesize, though it's debated, that lead poisoning might have contributed to the fall of the Roman Empire.
Wow. And today, while lead isn't used in piping anymore, thankfully, its main use is in car batteries, right?
Primarily, yes. However, the continued use of leaded gasoline in some developing countries remains a major health concern, especially for children.
Why, especially children?
It profoundly impacts the development and functioning of their nervous systems. It affects learning ability, behavior. It's really damaging.
And it can start even before birth.
Yes, embryos can receive lead across the placenta from the mother, so exposure can begin very early. And while lead's health effects are often localized, think metropolitan areas, near smelters, old industrial sites,
Right.
the lead from gasoline has been uniquely dispersed across the entire globe. It's changed the background levels. The oceanic distribution of lead, for example, is substantially influenced by all that past gasoline use.
And we've seen direct, tragic impacts, like that case in Western Australia.
Yeah, thousands of birds killed, water supplies contaminated, all from lead concentrate dust blowing off ships during transport. A stark reminder of the handling risks.
Okay, shifting to mercury, Hg, also known as quicksilver. It's such a peculiar metal.
It really is.
Liquid at room temperature, naturally occurring in its pure form sometimes, named after the Roman god, the messenger.
A fitting name? Maybe.
Yeah.
But mercury is not essential for life
I
at
don't
all.
know.
And it's highly toxic, especially, again, to the developing nervous system.
And like lead, it can cross the placenta.
Yes, human embryos can receive mercury across the placenta, potentially causing persistent mental development damage. But the most alarming aspect, perhaps, is its transformation in the environment.
What happens?
Under certain conditions, often involving bacteria in aquatic sediments, elemental mercury can transform into highly toxic, bioaccumulative methylmercury.
Methylmercury, that sounds familiar.
It should. And this methylmercury can then be transported over long distances, often through the atmosphere.
And this is exactly what happened with Minamata disease, wasn't it?
Precisely. It first made headlines in Japan back in the 1950s and 60s. A plastics plant was discharging untreated effluent containing methylmercury chloride directly into Minamata Bay.
And it got into the food chain.
It contaminated the entire ecosystem through marine species, fish, shellfish. Over 2,252 patients were officially diagnosed with this devastating neurological condition, and more than 1,000 died.
A terrible tragedy. And it highlights biomagnification, right, where the toxin concentrates up the food chain.
Exactly. Tiny organisms absorb a bit of mercury, then small fish eat many of those organisms, then bigger fish eat many small fish, and so on. Each step up the food chain, the mercury concentration increases, reaching dangerous levels in top predators like sharks or barracuda, often too high for safe human consumption.
Yeah, you mentioned a counter-narrative, something about Spain.
Yes, what truly fascinates me here is the case of the Almaden mine in Spain. It's been the world's principal mercury producer for over 2,000 years. A huge source.
2,000 years.
Yet, the region has experienced negligible environmental effects related to mercury poisoning. Local people consume fish from nearby rivers without getting sick.
So, why the difference?
It suggests the mechanisms for generating that really dangerous methylmercury are far more complex than initially thought.
Yeah.
It probably involves very specific environmental conditions, the right kind of bacteria, the right chemistry that just aren't present everywhere, even near a massive mercury source like Almaden. It's not automatic.
That's fascinating. Okay, from these ancient notorious elements, let's explore some more modern industrial workhorses. Arsenic. AS, for instance.
Arsenic. Its primary use today, maybe surprisingly, is in wood preservatives. So its demand is actually tied quite closely to home construction.
Huh. I wouldn't have guessed that.
Pure arsenic itself is rare. It's usually found as inorganic arsenic, often combined with oxygen, chlorine, or sulfur. Now, there's also organic arsenic.
Like in food?
Sometimes, yeah.
Oh.
Found in some seafood, like certain lobsters, for example. It's generally much less toxic, even in amounts that would seem lethal if it were the inorganic form.
Okay.
But large doses of inorganic arsenic, that's the notorious poison. And chronic exposure is linked to skin and lung cancers.
Okay, next up. Cadmium. CDS discovered later in 1817.
Yes, by Friedrich Strohmeyer, as a byproduct of zinc refining. And that's the key thing about cadmium. It's actually entirely a byproduct.
Nobody mines specifically for cadmium.
Nope. It comes from smelting zinc, lead, and copper ores. It just happens to be there.
And its uses.
It has a variety. Historically, pigments surprisingly prominent in some Van Gogh paintings, giving those bright yellows and oranges.
No kidding. Van Gogh used cadmium.
He did. Also used in stabilizers, coatings, special alloys, electronic compounds. But today, over 80% of its use is in rechargeable nickel-cadmium batteries, nightstick batteries,
Ah, okay.
and health effects.
Cadmium tends to accumulate in the kidneys over time, potentially leading to dysfunction. Intake is generally through diet. It can be taken up by plants like vegetables, corn, and also fish. Smokers also get a significant dose.
So is it a major public health issue?
Generally, adverse effects are not typically encountered from general population exposure under normal conditions. It's more of an occupational hazard or an issue in highly contaminated areas.
Got it. How about chromium? Cr. You mentioned it earlier with the essential versus toxic forms.
Chromium is a hard steel gray metal, highly resistant to oxidation, which makes it great for plating alloys.
Like chrome dumpers.
Yep.
Exactly. Used in metallurgical, chemical, and heat-resistant industries. A fun fact. Small amounts of chromium are what give emeralds their distinctive green color.
Oh, cool.
But again, we see that dual nature. Chromium, Cr3, the trivalent form, is an essential trace element, vital for glucose metabolism.
It's a good kind.
But exposure to large amounts of Cr key compounds, the hexavalent form, it can cause chromium allergy, skin issues, and it's widely assumed to be carcinogenic.
And where does the Cr come from?
Diverse sources, combustion, metallurgical industries, natural leaching from rocks, but also industrial processes like electroplating, leather tanning, and textile production.
Okay. And finally in this group, let's talk copper, another ancient one.
One of the very first metals known to humankind, yes. Named after Cyprus, a major source in antiquity. It's incredibly versatile and durable.
Properties.
Oh, it's non-magnetic, highly conductive, thick wiring, ductile, malleable, resistant to corrosion, and interestingly, biostatic, meaning bacteria don't grow well on it. It's truly at the heart of almost all modern technology.
And biologically, is it essential?
Absolutely. And here's a crucial point about copper's biological role. It's an essential nutrient. Adults need about 1 to 2 milligrams daily.
Okay.
What's more, copper deficiency is actually a much greater global health problem than copper toxicity.
Really? Deficiency is worse than toxicity.
For copper, generally yes, on a population level. Acute copper poisoning is rare, usually from accidentally drinking copper solutions, like from contaminated water pipes or containers. But those solutions are powerful emetics. They make you vomit forcefully, which limits absorption.
Ah, a built-in defense mechanism?
Yeah, and chronic poisoning is also very rare because the liver is quite efficient at excreting excess copper.
But it can be toxic to other things.
Yes, much more so to plants and some freshwater aquatic life, especially phytoplankton. That's why it's actually used as an herbicide and fungicide in specific agricultural applications.
Interesting balance there. Okay, let's pivot dramatically now from the ancient and industrial metals to an element that truly defines the atomic age, uranium.
Uranium, named after the planet Uranus, which was discovered around the same time. And it's actually more abundant in the Earth's crust than silver, cadmium, or even mercury.
More common than silver, wow.
Yeah, but for over a century after its discovery, it remained little more than a curiosity. Its main use was for making vivid green glass, believe it or not. Vaseline.
Glass, huh. Then came its pivotal role, obviously.
Obviously. Uranium-235 was the first element in which nuclear fission was observed. It's the basis for nuclear reactors, which currently produce about 1/6 of the world's electricity.
And the energy density is huge, right?
Immense. To give you a sense of its power, 20 kilograms of uranium, about 44 pounds, can produce the same energy as 400,000 kilograms or 400 tons of coal.
That's incredible.
Nuclear power also produces far less waste volume than burning fossil fuels. But of course, that waste is far more hazardous, and finding a safe, accepted long-term disposal system remains a major challenge.
So let's talk radioactivity. Pure uranium itself isn't that intensely radioactive, is it? I've heard a lump of pure uranium gives off less gamma radiation than a chunk of granite.
That's generally correct, at least for the pure element itself in solid form. Its major isotope, U-238, has an incredibly long half-life, about 4.5 billion years, roughly the age of the Earth, so it decays very slowly.
And U-235, the fissile one?
That has a shorter half-life, about 700 million years, and does emit gamma rays. But the primary radioactivity hazard from pure uranium itself is alpha radiation, mainly if it's inhaled as a dry powder. It's also chemically toxic, similar in toxicity to lead, separate from its radioactivity.
Okay, so the pure stuff is one thing, but the hidden danger you mentioned earlier comes from its decay products.
Yes, the dangerous children of uranium, as you put it. This is where it gets truly unsettling, especially concerning mine waste.
How?
Uranium ores don't just contain uranium, they contain a whole chain of over a dozen other radioactive elements that uranium decays into over time. These are harmful to living things.
And these aren't uranium anymore.
No. In fact, the very gamma radiation detected by geologists using Geiger counters when searching for uranium deposits often doesn't come primarily from the uranium itself.
Really?
It actually comes from associated elements further down the decay chain, like radium and bismuth, which are decay products of uranium that build up in the ore.
Okay, so what are the key problematic decay products?
The most important ones from a long-term hazard perspective are thorium-230, radium-226, radon-222, which is radon gas, and then the radon progeny.
Progeny, like children of radon.
Exactly. Imagine a string of dominoes falling. Uranium decays eventually to thorium-230, long half-life 80,000 years, which decays to radium-226, half-life 1,600 years.
Still pretty long.
Which then decays to radon-222, which is a noble gas. And then that gas decays relatively quickly into tiny, solid radioactive particles known as radon progeny. These include isotopes of polonium, bismuth, and lead.
And these have no value.
None at all. When uranium is extracted and processed, these decay products are unfortunately left behind and discarded with the mine wastes as tailings.
So radon gas itself, if you inhale it, it's a gas, you mostly exhale it.
Yes, radon gas itself is chemically inert and easily exhaled. The risk is lower. But it's those tiny, solid radon progeny that are the real insidious problem, especially in poorly ventilated spaces like underground mines or basements built near tailings.
What do they do?
These solid radioactive byproducts, often attached to dust particles, are inhaled and can get lodged deep in the lung lining.
Okay.
There, they don't get easily exhaled. And they continue to decay, bombarding the delicate lung tissues directly with damaging alpha particles, but also beta and gamma rays. This causes inflammation, fibrosis, scarring, and significantly increases the risk of lung cancer.
And this is a long-term problem.
Because the radon gas is continuously being produced by the decay of radium-226 with its 1,600-year half-life and its parent thorium-230, 80,000-year half-life, still present in the waste. So the hazard persists long after uranium mining ceases.
Decades, centuries.
Millennia, potentially. The U.S. EPA estimated back in the 80s that the uranium tailings deposits existing then could cause around 500 lung cancer deaths per century in the future if no countermeasures were taken to contain them.
That's sobering. And as a grim, real-world example of one of these progenies, we saw the case of polonium-210 recently, didn't we?
Yes, polonium-210, a rare and highly radioactive metalloid infamous for causing Alexander Litvinenko's widely publicized death by poisoning in London in 2006.
And it's incredibly potent.
Extremely. It's deadly in minute amounts. Theoretically, just 1 gram could poison millions of people if ingested or inhaled. It's a powerful alpha emitter.
Where does it come from? Is it common?
No, polonium-210 is extremely rare in nature because it has a short half-life, about 138 days. It's mainly produced artificially in milligram amounts by bombarding bismuth with neutrons and nuclear reactors, primarily, it seems, in Russia.
Okay, before we wrap up, let's briefly touch on a material that isn't a metal, but raises many similar environmental and health concerns related to mining and human use: asbestos.
Yes, asbestos. It's included in our source material because the issues surrounding it mining impacts, processing risks, long-term health effects from exposure, disposal, mirror many metal-related concerns.
So what is asbestos exactly?
It's actually a commercial term, not a single mineral. It refers to a group of 6 naturally occurring fibrous silicate minerals. They fall into 2 main groups: the serpentine group, which includes chrysotile, the most common type, and the amphibole group, like amosite and chrysotillite.
And for a long time, it was seen as a miracle material, right?
Absolutely. And you can see why from its property.
Like what?
It's incombustible, doesn't burn. It's thermally stable, great insulator. It's resistant to biodegradation and most chemicals. It has low electrical conductivity. And critically, its fibers are strong, yet flexible. And they can even be spun into yarn or mixed into materials.
So it had countless uses.
Oh, tons. Fireproof fabrics, pipe insulation, boiler lagging brake linings, clutches, roofing shingles, cement pipes and sheets, floor tiles. The list goes on and on.
However, the dangers soon became apparent.
Indeed. The dangers of airborne asbestos fibers have actually been known, or at least suspected, for well over a century. Deaths and serious lung problems were observed in asbestos mining towns even before 1900.
That early?
Yes. The first medical diagnosis linking deaths specifically to asbestos exposure, what became known as asbestosis, was made in 1906. By 1918, some insurance companies reportedly would no longer even insure asbestos workers due to the known risks. And by 1935, there was a strongly suspected link to lung cancer.
And yet, its use continued and even expanded.
Tragically, yes. Despite this mounting scientific data, the dangers were, for a long time, largely ignored or downplayed by many manufacturers and users. Companies continued to use it extensively, sometimes even favoring it over potentially safer alternatives like fiberglass, simply because asbestos was cheaper. This led to widespread, needless exposure for workers and the public.
And this exposure is associated with specific, serious diseases.
Yes, primarily 3. Asbestosis, which is a scarring of the lung tissue making breathing difficult, lung cancer, especially synergistic with smoking, and mesothelioma, a particularly aggressive cancer of the lining of the lungs or abdomen that is almost exclusively caused by asbestos exposure.
And these take time to show up.
A very long time. These diseases typically have a very long latency period, usually 20 to 40 years, sometimes even longer, between initial exposure and the onset of symptoms or diagnosis. This delay made it harder to initially link the cause and effect, and means we're still seeing cases today from exposures decades ago.
This unfortunately led to what our sources call the litigation elephant, didn't it?
Yes, the longest and most expensive mass tort litigation in U.S. history by far. By 2007, it involved over 700,000 claimants and around 8,000 defendant companies. The estimated total costs were projected to exceed $250 billion.
$250 billion.
And the no-win, no-fee model used by some lawyers in the U.S. legal system certainly played a role in driving the sheer volume of claims.
There was controversy around that, about legitimate versus maybe less legitimate claims.
There was. President George W. Bush, for instance, stated that compensation funds should focus on those who are genuinely sick, not primarily benefiting lawyers or claimants who aren't actually ill. And one law professor, Brickman, noted quite critically that while perhaps 100,000 workers tragically died from asbestos diseases, the legal system turned it into a money-making machine, involving many baseless claims alongside the valid ones.
But the source emphasizes.
Crucially, yes. The source emphasizes that this litigation controversy, however complex, should absolutely not overshadow the underlying reality. A quiet, sad, and directly related crisis in public health, an epidemic of asbestos-caused diseases that has claimed, by one estimate, the life of 1 in every 125 American men over the age of 50.
1 in 125, that's a staggering statistic, a truly sobering perspective on the human cost.
It really is.
And it's worth noting quickly that modern asbestos products, where they are still used under strict controls, are very different from the old ones.
Yes, that's an important distinction. Pre-1970s products were often dusty. Friable, meaning they crumbled easily, releasing fibers, and frequently contain the more hazardous, amphibole types of asbestos.
And today?
Today, where asbestos is still permitted, banned in many countries, generally only chrysotile is used, and it's typically incorporated into dense, non-friable materials where the fibers are locked or encapsulated within a matrix, like in chrysotile cement pipes, sheets, or shingles.
So the risk of fibers becoming airborne is much lower.
Significantly lower, yes, provided the material isn't sawed, drilled, or damaged improperly. That encapsulation makes a big difference in reducing potential exposure during normal use.
Okay, so wrapping this all up, what does all of this mean for us? Today, we've taken a really rigorous look at metals and also asbestos as a related mineral. We've seen how these elements are fundamental building blocks, absolutely essential to life in many cases, and yet also capable of significant harm, often made much worse by human activities, by how we mine them, use them, and dispose of them, with consequences that can last for generations.
Yeah, what really stands out to me is that delicate balance of concentration required for the essential elements, that narrow window between deficiency and toxicity, and also the stark reality that, unlike so many pollutants we worry about, metals persist. They don't degrade, they just change form and location, cycling through the environment potentially forever.
So, as you, our listener, go about your day, consider how truly intertwined our lives are with these elements. Maybe it's a surprising fact that our use and disposal habits are often bigger environmental culprits than the mining itself for many metals.
Or perhaps the quiet, almost invisible threat of those long-lived radioactive decay products accumulating in mine waste.
How does this new understanding of metals, their necessity, their persistence, their potential for harm, their complex chemistry, how does it shape your view of the world around you? And what does it tell us about the ongoing challenge of living sustainably with these powerful permanent elements on our planet?